So welcome to Robotics 1. In today's class, we are going to, what I'm going to do is I'm going to discuss forward and inverse kinematics of a very, very famous robot, which is called as the Skera robot. And why is this robot important? Because this robot is used in almost all pick and place operations. It is one of the simplest robots to implement. If you are working in a semiconductor industry, if you happen to get a job at TSMC or Intel, you would see these robots on the assembly line, wafer handling. So if you are gonna get a position at robotics engineer or automation engineer, if you are gonna get interviewed at TSMC or NXP or Intel, I guarantee you they will ask you about Skera robot. So I'm gonna work out the forward inverse kinematics of Skera. Then in last class, I worked out two robots. I actually did the forward kinematics for both the robots, including the spherical wrist. Today, I will go on to the MATLAB and I will explain how the MATLAB forward and inverse kinematics implementation works. Last but not least part is I will talk about how to perform velocity analysis and the definition of Jacobian. So these concepts are extremely important. So next week, unfortunately, I won't be able to meet you because it will be fall break. But week after next, when you come back, then we will start with the robot dynamics and control. So by now, everyone should be expert in rules. Remember the rules? Okay, so I'm going to draw Skera robot. When you go to lab, I can show you how an actual Skera robot looks. The DoBot that you have played with is R perpendicular R, parallel R type of robot. If you look at the Skera robot, there are two configurations possible. One classic configuration for the Skera robot is something like this. So what you have is you have R, and then what you have is you have P. So you have R, and P, R, and P. So this is the first revolute joint. This is the second revolute joint. And third joint is a prismatic joint. First revolute joint, second revolute joint, and the last one is a prismatic joint. So the prismatic joint has a cylindrical actuator or the lead screw that can go up and down. So first revolute joint, second revolute joint, it goes to the actual position. The lead screw comes down. There would be a suction cup or a gripper. It will grip and then go to the position where it needs to be placed. Skera robots are very, very fast and they are commonly used in pick and place or assembly operations. Now, what I'm going to do is I'm going to start with the coordinate system, Z0. So tell me the rules. What is rule number 1? Through joint. Second, XN intersect Zn minus 1. It goes without saying that Xn is perpendicular to Zn. The last, right hand coordinate. Everyone understood this? So this is my first joint. This is my second joint. And the third joint it can go down or it can go up. For the sake of simplicity, I'm going to assume up. Do you agree with me? Z1, Z2, Z1, oh, Z1, Z2, and I would use this as Z3. Okay. Next, X. Since that we don't have any other joint before the first revolute joint, X naught does not matter. So this is going to be my X naught. Now tell me, where should be my X naught, X1? Can you agree this will be my X1? Because this satisfies the rule. X1 perpendicular to Z1, X1 intersecting Z0, and X1 is perpendicular to Z0. You guys agree? Next, I'm going to assume this as X2. Do you agree the rules are satisfied? And the last but not least, I'm going to assume X3, something like this. Now, I want you to notice, deliberately, I have chosen the coordinate system, which is the 0th frame, first frame, second frame, and third frame. They are similar to each other. You agree with me? And why did I do that? X, Z. Can someone tell me why did I choose my coordinate systems like this? All coordinate systems align with each other. Do you agree with me? What does it do? All projection matrix become identity. Everyone understood this? So I'm gonna start with this guy, theta 1, theta 2, and typically the extension is treated as D3. D3 stands for displacement. First joint, rotation theta 1, second, and the extension is D3. I'm gonna add A0, A1, I would add this as A2, I would add this as A3. And I'm going to assume A4 is equal to 0 because whatever extension that I'm going to have is the extension of D3. You can also add A4, doesn't matter, but I'm just going to treat as D4. So first revolute joint, rotation matrix, 0R1. What is it? Zero, zero, one. You agree with me, my projection matrix is an identity matrix. Everyone understood why projection matrix is an identity matrix? All coordinate systems align with all coordinate systems. So 0h1 cosine theta 1 theta 1 0 sine theta 1 cosine theta 1 0 0 0 1 0 0 0 1, and tell me what should I write here? This is the distance between the frame number 1 and frame number 0 in the coordinate frame of frame number 0. In other words, how do I go from 0th frame, which is here, to the first frame, which is over here, along the coordinate system of the 0th frame? So I need to go A0 up in the z-axis, and that distance you need to have the valid x and y for all theta 1s, and by now you should know this would be A1 cosine theta 1, A1 sine theta 1. Any questions here? Because if you look from top, the two coordinate system, the two you are going to see x0, you are going to see y0. When your theta 1 is 0, you are here. When your theta 1 is somewhere here, then you are going to have x coordinate as A1 cosine theta 1, and the y coordinate A1 sine theta 1. Do you agree with me? Next part, 1R2. Tell me the rotation transformation. By now you should know this. Cosine theta 2 minus sine theta 2, 0. Sine theta 2, cosine theta 2, 0, 0, 0, 1. Yeah, so let me just, projection matrix is going to be an identity. Why? Because frame number 2 is aligned with frame number 1. So 1H2 cosine theta 2 minus sine theta 2, 0. Sine theta 2 cosine theta 2, 0. 0, 0, 1. 0, 0, 0. And can you tell me what should be in the first row, fourth column, second row, fourth column, third row, fourth column, and fourth row, fourth column? Fourth row, fourth column will be 1. What should be in first row, fourth column? Then very good. Now last part, and let me see who can tell me the answer for this. What is 2R3? What is 2R3? R3, is there any revolute joint? No, no revolute joint. It means it has to be an identity matrix. For all prismatic joints, the rotation matrix is an identity matrix. So, and then one word of caution. Even though rotational matrix is an identity matrix, it may be possible that your coordinate systems are not aligned. I'll tell you what I mean by not aligned. If my Z3 is going down, Z2 and Z3 would be in the same direction, but the signs would be opposite. You agree with me? There is a reason I assume Z3 is in the same direction as Z2, so that you get identity. If Z3 goes in the opposite direction, you will have to flip the sign. Everyone understood this? So even your rotation matrix in the identity, unless your axes are aligned perfectly, the projection matrix will not be an identity. Everyone understood this?
The opposite side with the third row, third column.
So again, what you need to do is always remember this procedure, okay? And that's why I have been explicit in writing this. Projection of 3, x3, y3, z3 on projection of 2, x2, y2, z2. If your z3 is flipped, right now it is like this. If your z3 is flipped, you will have to flip other axes also. Your y will also be flipped because it will no longer be right hand coordinate system. You want me to flip it and show it to you, or you got it? So now, because you can't flip z3, and then your y3 will come outside, which means you are going to have minus sign in z3 and y3. Everyone understood this? Okay. All right. Now comes the homogeneous transformation. 2h3 and 2h3 0 0 1 0 0 1 0 0 0 1 0 0 0. We get 1 here. Now I have assumed the offset to be 0. So now if you look at x, can you see x are aligned? So 0. y2 and y3 are aligned. You agree with me? This is y3. y2 and y3 are aligned. And z2 and z3, recognize you need to go minus d3 to reach to the last frame. You agree with me? So this will be minus d3. Everyone understood this? Any question about this transformation? And your forward kinematics would be 0h3 is equal to 0h1, 1h2 and 2h3. Are you with me so far? Once your forward kinematics is done, we use MATLAB solve function, or you can use Python, NP-solve, any other function to solve the inverse kinematics problem. But sometimes the inverse kinematics problem may be ill-conditioned. I will tell you what it is. So you will find out 0h3. 0h3 will give you the rotation transformation. So it will give you something like this. It will give you 0r3. And then it will give you px, py, pz. What is 0r3? 0r3 is the absolute rotation of the end effector with respect to the 0th frame. Now, how do you debug this? Now, the easiest way to do this is use the MATLAB command ROTM. So rotation matrix ROTM to Euler, EUL, and then supply this rotation matrix 0r3, and that will give you roll, pitch and yaw. Are you with me? Because please try to understand, as human beings, it is very difficult for us to visualize the rotation matrix. but I can clearly visualize what is yaw. Yaw is the rotation about Z naught. Yaw is the rotation about Z naught. Pitch is the rotation about Y naught. And roll is the rotation about X naught. So based on that, I can identify. Now, many a times I want you to realize that you want to have kind of an intuition to the answer that you are getting. Okay, and what do I mean by that? If I ask you, and I want you to build this will actually help you a lot. If I ask you now, rotation matrices, homogeneous transformations are fine, but I want you to look at this problem. Just look at this problem and tell me Px, Py, and Pz. Just look at the robot and tell me what would be the Px, what would be the Py, what would be the Pz. How many of you can think about it? You don't need pen and paper. Like set the robot and just find out. Z is A naught. So Z, you guys agree with me? So let's start with Z. It's very simple, right? So A naught is positive. A2 is positive, and then you are coming down by D3. You agree with me? So with respect to this coordinate frame, so if I want to find out the location of this end effector in Z, so Z, this is going to be A0 plus A2 minus D3. Do you agree with me? Simple. Now what would be about X and Y? Remember, to find Z, we look in the front view. To find X and Y, you need to look in the top view. In the top view, what do you see? You guys know this. We have done this many times. And everything needs to be with respect to X0 and Y0. X0 and Y0. You agree with me? So let's assume that you have rotation theta 1 and rotation theta 2. Does it look similar to you? It is similar to the very first problem I solved. A1 and A3. So this angle is theta 1. So what you have here? You have A1 cosine theta 1, and here you have A3 cosine theta 1 plus theta 2. You agree with me? Yes or no? What you have here? A1 sine theta 1. Similarly, here A3 sine theta 1 plus theta 2. You agree with me? So you solved forward kinematics problem without even using any mathematical things. No MATLAB. Now you can verify if your answers are correct or incorrect using MATLAB. But before I go there, I want you to look at these equations very carefully. These equations are ill-conditioned. And since you are taking linear algebra, you probably know what it means. So Px is equal to A1 cosine theta 1 plus A2 cosine theta 1 plus theta 2. Py is A1 sine theta 1 plus A2 sine theta 1 plus theta 2. And Pz is, I'm going to use a different color, A0 plus A2 minus D3. You agree with me? Oh, yeah, A3, sorry. A3, correct. Is it right? You agree with me? So why do I say, okay, let me ask you, how would you solve an inverse kinematics problem? You have three unknowns, theta 1, theta 2, and D3. You agree with me? If you use what we have been doing for last few problems, wherein we use a solve function, provide three equations, ask for three unknowns, you think you will get the correct answer. You think you'll get the correct answer. No. Why? Because please try to understand. D3 is independent of theta 1 and theta 2. Which means if you use any numerical solver, there is possibility that it may not give you correct answer. Because to find D3, you just need to substitute D3 is equal to PZ or A0 plus A2 minus PZ is going to give you D3. You agree with me? D3 is independent of theta 1 and theta 2. And to solve inverse kinematics problem, you need to supply two equations, Px and Py, and ask for theta 1 and theta 2. Once again, I will tell you that when we work out the inverse kinematics problem, I will show you what happens if you provide a three condition system with a solver. If you use MATLAB psolve function for finding out theta 1, theta 2, and D3 by supplying Px, Py, Pz and asking for theta 1, theta 2, and D3, that function will not give you correct answer. Because this actually, whenever you are solving this, D3 does not depend. So it's not a simultaneous equation solving problem. D3 does not depend upon Px. D3 does not depend upon Py. It's completely independent. You agree with me? So when we look at the forward kinematics equation, before you implement your inverse kinematics, look at the equations and see what coupling exists between equations before you blindly use any Python solver or a MATLAB solver. Everyone understood this? Everyone understood this? Yeah.
So what is exactly D3? Is it the length?
D3 is the extension of the cylinder of the prismatic joint.
That is some sort of value
You basically supply theta 1, you supply theta 2, and you supply D3 from the controller. For a Skira robot, you can visualize the workspace is a cylindrical workspace. So Skira robot can reach within the cylindrical workspace. Any other questions? Now, one last thing which I want to talk about, and then we will start. Everyone understood the forward kinematics of Skira robot? Okay. Now, one thing I want to talk about is velocity analysis. Velocity analysis. And I'm going to start with a very, very simple case. I'm going to start with a very, very simple case. So this is the 1 degree of freedom robot. This is the 1 degree of freedom robot, theta 1. You agree with me? Since it's a planar robot, Pz is equal to 0. It has x naught, it has y naught. X naught, if I were to consider this A0 cosine theta 1 and A0 sine theta 1. You agree with me? So you have A0 cosine theta 1. So Px is going to be A0 cosine theta 1. Py is equal to A0 sine theta 1. If I want to find out the velocity, what should I do? Differentiate. And what is the differentiation of Px? Now note, we are differentiating with respect to t. Theta depends upon t. So dpx by dt is d by d theta 1 of a naught cosine theta 1 multiplied by d theta 1 by dt. You agree with me? Because understand, Px is the dependent variable. Px depends upon theta 1. But theta 1 is not an independent variable. Theta 1 is also a dependent variable because theta 1 depends upon time. So you do the first derivative with respect to theta 1, multiply it by the derivative of theta 1 with respect to time. Everyone understood this? So this equation is going to look like a naught is a constant. Derivative of cosine theta 1 is minus sine theta 1. D theta 1 by dt is theta 1 dot. Now I would do dpy by dt. Please note, same logic, d by d theta 1, a naught sine theta 1, d theta 1 by dt. So you have to use the chain rule. And even if you don't remember this, MATLAB will do it for you, but I want you to understand this is going to be a naught cosine theta 1 dot. And for the sake of discussion, let me do dpz by dt, and clearly this is going to be 0 because we are talking about a planar case. Do you agree with me? Any questions here? Yeah, you can actually, so I'm solving this problem. Prismatic joint has velocity. I completely agree with you. But I'm doing velocity analysis for this single length. So it's just a planar length. Okay, I'll work out prismatic joint in next class, but I want you to understand. Everyone understood this? Any questions the way I worked out the derivative? Okay. But I want to express this in a slightly different fashion. I want to use, so this is my equation 1. This is my equation 1. This is my equation 2. And I'm going to call this my equation 3. Okay. Equation 1, equation 2, equation 3. I want to write this equation in a matrix form. So the way I want to write this equation is Px dot Py dot is equal to a matrix multiplied by theta 1 dot theta 2 dot. Why am I writing it like this? Because please try to understand, this guy is end effector velocity. And this guy is the joint velocity. Do you agree with me? This is called as the end effector velocity. And please note, extremely important, theta 1 is in the 0th frame. Oh, this actually, there is no theta 1. So theta, only theta 1. Sorry. So theta 1. So what needs to happen is, check this out. I would do A naught sine theta 1, A naught, there will be a minus sign, A naught minus A naught sine theta 1, and I would have 0, can actually do 0 here, 0 and A naught cosine theta 1. Sorry, here, A naught cosine theta 1. Now what this means is, first row, first column, A naught sine theta 1, that gives you the first equation. Second row, first column, that gives you the second equation, A naught cosine theta 1 dot. Everyone understood this? The reason, so the reason this guy is expressed something like this, this is called as the Jacobian. What is a Jacobian? Jacobian is the matrix that relates joint velocities to the end effector velocity. So you have a joint velocity relating to the end effector velocity. So Jacobian relates joint velocity to end effector velocity. Okay, now I'm going to work out this velocity analysis for the Skera robot. I'm going to work out the velocity analysis for the Skera robot. If you look at for Px, we know, and let me get the terminology, A1 cosine theta 1, A1 cosine theta 1 plus A3 cosine theta 1 plus theta 2, Py is equal to A1 sine theta 1 plus A3 sine theta 1 plus theta 2, and Pz is equal to A naught plus A2 minus A3. So what are the variables? Theta 1 is function of time, theta 2 is function of time, D3 is function of time. Do you agree with me? So if I want to perform this derivative, I have to, let's do it. Px dot A1 cosine theta 1, can I write minus A1 sine theta 1 dot A3 cosine theta 1 plus theta 2, that will become first minus A3 sine theta 1 plus theta 2 theta 1 dot. You agree with me or no? And A3 is go, so you have to take the derivative of this whole term. So d by, so first derivative with theta 1 dot minus A3 sine theta 1 plus theta 2 dot. You agree with me? Yes or no? For my own satisfaction, I want to work out this derivative, okay? D by d of A3 just for my own satisfaction. Cosine theta 1 plus theta 2 is A3 d theta 1 cosine theta 1 plus theta 2 theta 1 dot plus A3 d by d theta 2 cosine theta 1 plus theta 2 dot. Okay. Next, Ty dot, same jugglery, A1 cosine theta 1 dot plus A3 cosine theta 1 plus theta 2 theta 1 dot plus A3 sine theta 1 plus theta 2 dot. Last but not least, Pz, A0 is a constant, A2 is a constant, so it's going to be minus D3 dot. Oh, yeah. Thank you. Cosine, right? Now, what I need to do is Px dot, Py dot, Pz dot is equal to this big matrix multiplied by the joint velocities. Px, Py, Pz are end effector velocities. And you have theta 1 dot, theta 2 dot, and D3 dot. Do you agree with me? And this guy is what? Jacobian. So how do I write Jacobian? So theta 1 dot, theta 1 dot. So this will become minus A1 sine theta 1 minus A3 sine theta 1 plus theta 2. This will become A3 sine theta 1 plus theta 2. This will become A1 cosine theta 1 plus A3 cosine theta 1 plus theta 2. And this guy, actually I made a mistake. I need to give it a little bit more space. Because here there is 0. Theta 1 dot, theta 2 dot, and D3 dot. And here I'm going to write A3 cosine theta 1 plus theta 2, 0, 0, 0, and minus 1. Some of you may ask me, what is the physical interpretation of Jacobian? Please try to understand. This is nothing but the Taylor series expansion. Now, what do I mean by Taylor series expansion? Let's try to look at the first problem. So, about that you have a curve, and what you do is the derivative is the slope of the line, and you multiply that by the delta x. You multiply by the delta x, and that gets you delta y. And in the case of Jacobian, your joint variable theta 1 dot is over here, and you are getting px dot onto y. So you have a function which is dependent on theta 1, which is px. Px dot is df of theta 1 divided by d theta 1 multiplied by d theta 1 by dt. And why is that? Because theta 1 is dependent on time. Theta 1 is a dependent variable. At the end of the day, your derivative needs to be with respect to independent variable. So what you have seen here, this is the slope, and this is nothing but the Jacobian. I want you to understand this very, very clearly. This slope indicates the influence of change in the independent variable to the function. There is only one theta 1. So this derivative is a full derivative, d by dt or d by dx. You agree with me? Because px only depends upon theta 1. Theta 1 depends upon dt. So this is a full derivative. You agree with me? Now imagine in the case of this particular the displacements. So you have px, which is dependent on theta 1 and theta 2. Py, this is dependent on theta 1 and theta 2. So you cannot use full derivative. What you will use is a partial derivative. And I want you to understand the physical interpretation of Jacobian. Imagine currently, if you have $100 and 50 cents, you have $100 and 50 cents. If I give you $1, your net worth is going to be $101 and 50 cents. You agree with me? Instead of giving you $1, if I give you 1 cent, you will have $100 and 51 cents. You agree with me? In other words, even though I'm giving you an increment or variation or change of unity, depending upon where it is influencing, the net worth changes. You agree with me? So theta 1 dot is influencing this much quantity in px dot. Theta 2 dot is influencing this much quantity in px dot. Theta 1 is influencing this much quantity in py dot. Theta 2 is influencing this much quantity in py dot. Theta 1 dot does not influence pz dot. Theta 2 dot does not influence pz dot. The only quantity that influences pz dot is minus d3 dot. Everyone understood this? Jacobian calculations are extremely important, because you'll realize many a times to find out the static forces, we use something called as the transpose of Jacobian, and I will prove it to you in next class. At this point, I want you to understand Jacobian, what Jacobian means, it relates joint velocities to the end effector velocities. Joint velocities are expressed in its individual joint axis. Theta 1 dot is about Z0. Theta 2 dot is about Z1. Z3 is about Z2. Everyone understood? Joint velocities are in the reference frame of each joint, but the end effector velocity will always be in the inertial or the first or zero frame, and this is the relationship between the Jacobian. Jacobian relates joint velocity to the end effector velocity. One thing I want you to observe: Jacobian depends upon the values of theta 1 and theta 2. At joint moves, instantaneous values of theta 1 and theta 2 change, which means the Jacobian is always changing as time goes on. Do you agree with me? Your theta 1 dot may be constant, your theta 2 dot may be constant. It means it is rotating at a constant velocity. But since the Jacobian values at that theta are different, your end effector velocity will be changing. Everyone understood this? How do we find Jacobians? We find Jacobian using math. So probably you have noticed that I passed on an attendance sheet today. So if the students who are already present, they got 10% bonus. Yeah, if numbers don't match, then everyone gets minus. So if you have proxy signed for your friend, get that attendance sheet back and scratch the name. Okay, now we are gonna go to MATLAB. Please open MATLAB. After a stressful midterm, you still came to class. Okay. Open the script Scira.n. Line number 1. We are doing forward and inverse kinematics of Scira. We are also going to do the velocity analysis of Scira. Line number 2 is blank. Line number 3, clear all CLC. We have 3 joint variables, T1, T2, and D3. I'm also specifying theta 1, theta 2, and DD3. And you will know why I did that. The values for the Scira robot, A0 is equal to 50, A1 is equal to 100, A2 is equal to 150. Homogeneous transformation. This homogeneous transformation is the same homogeneous transformation that I derived. Yeah, and nomenclature is also the same. So this is the same homogeneous transformation that I derived a minute ago. H23, you have the same homogeneous transformation that I derived a minute ago. And I want you to notice H23 is an identity matrix with a minus D3. and count the number of fields. Oh, you didn't get a, they didn't get that. Okay. So now what you'll do is H03 is equal to H1, H01, H12, H23. And then you would extract first row, fourth column, second row, fourth column, third row, fourth column from H03. Then TT1 is I'm substituting one value of theta 1. TT2, I'm substituting one value for theta 2. And D3, actually I'm saying theta 3, but it's a displacement. So D3 is the displacement of the prismatic joint. Then I use VPA, that stands for variable precision arithmetic, substituting TT1 in place of T1, TT2 in place of T2, and D33 in the place of D3. Why is that? Because my forward kinematics equation will be in terms of T1, T2, and D3. It's a symbolic expression. I want to replace those symbols by numbers. And those numbers are 0, 35, and 50. That's why subs is used. Now, PY new subs is PY T1, T2, D3. And last but not least, you are using PZ and you are substituting these numbers. Everyone understood this? Now, I want to show you what I have done. This is the mistake I deliberately made so that provide. Here I'm trying to find out the inverse kinematic solution for theta 1, theta 2, and DD3 by supplying Px, Py, and Pz. But remember, in the discussion, I said D3 does not depend upon theta 1 and theta 2. It's a very simple substitution. But I'm actually trying an ill-conditioned system where ideally what I have is I have two variables, two equations, one variable, one equation. D3 can be found out from the equation for Pz, but theta 1 and theta 2 you need to substitute, you need to supply Px and Py. Everyone understood this? So I'm trying to use inverse kinematics in a wrong fashion without thinking. And I want you to run this code and see what happens. So if you copy this code from all the way here to here, right click, evaluate selection, then you will realize that you may get some garbage answer. So you will get, now if you want to get the correct answer, then what you need to do is you need look at the correct answer. You need to find out theta 1 and theta 2 from Px and Py, and last which is D3 from subtracting A0 and A1 from P. Yeah. So A2. Great. Thank you. Everyone understood this? Please run this code. And if you are using the latest and greatest version of MATLAB, probably PSolve is now smarter, so it can solve the condition system. But if you are using an older version of MATLAB, you may not get the correct answer. Story does not end here. This is where I'm finding the Jacobian. So what you have is Vx is the velocity in x direction. Vy is the velocity in y direction. And Vz is the velocity in z direction. Now, however, I need to be clear about what is my dependent variable and what is my independent variable. So that's why now I'm defining some symbolic variables, and I want you to notice how I define the symbolic variables. Symbolic variable theta1 in the parenthesis t, that means that depends upon t. Symbolic variable theta2 in the parenthesis t, which means theta2 depends upon t. And dr in the parenthesis t, which means now MATLAB knows that di is a symbolic variable that depends upon t. I replace t1 by theta1, t1 by theta2, and d3 by di. So now MATLAB knows Px depends upon theta1, but theta1 depends upon t. Py depends upon theta1 and theta2, but they depend upon t. So which means finally, when I do the derivative Vx, Vy, Vz, this is my independent variable. T is the only independent variable. Theta1 depends upon t. Theta2 depends upon t. P depends upon t. But Px depends upon theta1 and theta2. Py on theta1, theta2. Easy on D3. Everyone understood this? Which means when I run this code, I would get the velocity analysis. Now, one thing I want you to notice, that MATLAB will give you minus diff d1tt. This stands for d3 dot. Here you will see diff theta1 tt, that is theta1 dot. You will see diff theta1 t, this is theta1 dot. And this exactly same as the equation that I derived. Everyone understood this? Now, if I want to find out acceleration, then what? Very good. Everyone understood? If I want to find out the acceleration, I will do the same process, but now I would take a derivative of velocity. Now I want to solve the dynamic problem. Then what? Force is equal to mass times acceleration. Torque is equal to mass moment of inertia multiplied by angular acceleration. That's it. After you come back, we'll rested, refresh from all break, we'll start dynamics. And then clearly the robot, as you know, is inherently unstable. So you would have to add control. How do you control? If you want to control x dot, y dot, you don't have any control on end effector. Nobody is physically going to control the end effector. You would just control theta1 and theta2, theta1 dot, theta2 dot, and that's it. That's the control of it. Well, before I conclude for today, there is one more minute. So I want you to look at forward and inverse kinematics. In this code, I have given you the MATLAB code for R perpendicular R parallel R, which is the do-bot or do-bot. Go down and you would see the Skera robot that I just worked out. And the last but not least is this is the spherical wrist, wherein you have R perpendicular to R, perpendicular to R, and I have solved spherical wrist over here. Again, in spherical wrist, you have the same issue. You can get an incorrect solution, and then you want to be very careful with the way you calculate thetas, but I'm sure that you'll be able to figure this out. With that, I'm going to stop here. Tatvik, do numbers match? Before you leave, numbers match? Check out them. Call their names out.
Vishal Sasikumar, Rahas Guru Datta, Shivam Sharma.
Any other questions you have, Tatvik? Can we let them go? Can we dismiss the class? Okay, class dismissed. And you got 10% bonus for attending the class.